All right, we want to consider the settlement of a structure instead of just a fill. So let's take a look at the aspects of analyzing a structure. So just as an example here, I've got my t equals 0 minus situation. In this case, I have sand over clay. And then my t equals 0 plus to t equals infinity situation. I have my structure in place. And so in other words, we're going to build the building at t equals 0 plus, and we're going to leave it there for time infinity. And what we're going to find is going to happen is that when the structure settles, when settlement takes place, it's not going to take place evenly. In other words, we're going to find that the center of the structure is going to settle more than the edge of the structure. So that's what we're going to learn, and we'll see why here. One of the things that we need to do is we need to determine the stress increase due to the building weight. So let's think about it conceptually. So I have my structure here, the ground surface is here, and I'm going to consider various points below the structure. Point A, point B, point C, and point D. And we want to think this through a little bit in the sense that what would be the relative strength in stress increases due to the weight of the building at these various points. Well, what we find, let's take a look at point D over here, because that's the easiest one to see in a sense. In other words, the building weight is here, so I'm applying my load over here, and point D is way off to the side here. I think you can imagine that point D will not feel much stress due to the weight of that building. Why? Because it's so far away. It's off to the side. Similarly, we're looking at point C. Well, the weight of the building is here. Now, point C is deep in the ground. And here's a concept of why you might envision that you're not going to feel it, or point C will not feel that stress very much, and that is that it's far away. So one thing that you can do is, take your hand. Let's say this is your hand here. There's your hand. Not a very good drawing. But let's just say that's your hand. And on the back of your hand, apply a load with your other hand. Press your finger down. And what you're going to find is that where will you feel that load? Well, you're going to feel that load pretty much in this region in here. You're not going to feel the load at the bottom. So that is my point C. My point C does not feel that load simply because it's far away. The same reason you don't feel anything. It's farther away at the bottom of your hand, and your load is at the top of your hand. So what we're going to find is that point C doesn't feel very much, point D doesn't feel very much. And now let's compare points A and points B. Well, point A is below the center of the structure and is up and close. Point B is below the edge of the structure. So naturally, I think you can, from just a gut feeling and intuition, that point B is going to feel less than point A simply because it's below the edge rather than below the center. So if I compare these, what we're going to call the delta sigma V at point A is going to be that greater than B, going to be greater than C, going to be greater than D. Now, people have figured this out, so I'm not going to go through and detail analysis of this because there's no reason for it. But we're going to use a standard solution, and I'll show you how to use it. So I'm going to show this. The best way is to show it with an example. And what we're going to do is we're going to find delta sigma V for, again, points A, B, C, and D. But now I'm going to give some details. I have my structure. The weight of the structure is 2,000 kilonewtons. My footprint, it's a 10 meter by 10 meter footprint. We're going to say, in other words, B is 10 meters. The width of the structure is 10 meters. And that, we're going to consider square structures. Structures with a square footprint. So to keep it simple, we're only going to do structures with a square footprint. But I will show you how you can handle other situations. Okay. The points that we're interested in is point A, which is at 4 meters below the center of the structure. Point B is 4 meters below the edge of the structure. Point C is 16 meters below the center, center of the structure. And point D is 3 meters past the edge and 5 meters deep. I'm going to define a coordinate system. We're going to measure x sub f from the center line of the structure. We'll measure z sub f from the base of the structure. And so we're going to start by making a table here, points A, B, C, and D. We're going to list the z sub f, which I just went through. And we're going to calculate z sub f over b, which b is 10 meters. So we have our z, 4 goes to 0.4, 16 goes to 1.6. We simply divide by 10. 5 goes to 0.5. We're going to list the x sub f for each point. In other words, A and C are 0 because they're down the center line. B is at the edge, which is 5 meters from the center line, and point D is 8 because it's 8 meters from the center line. And then we're also going to divide it by B, x sub f over b. So we divide those by 10, and these are our answers. We're going to create a Q. Q is what? Q is the surface stress. It's simply weight divided by the area. In this case, we have a 10 by 10, so the area is 100 square meters. The weight is 200 kilonewtons. And so we get that our Q is 20 kilopascals. All right, so now I'm going to show you the chart that forms the standard solution. Now, how do we read this chart? This chart is called a pressure bulb or a Boussinesq chart. I like to call it a pressure bulb. Why is it a pressure bulb? Because you can see the bulb shape in the curves here. Now, the way to read this is that a couple things. One, this tells me the footprint of the building. It's a square. And the width of the building is B. Then I have my surface stress, Q. And this surface stress, the way to look at this is here is the ground surface right here. And I have the stress applied there, that Q. And then everything, this is below the edge of my structure. This is below the other edge. It's symmetric. This is below the center of the structure. So you can see that I've plotted the points, and they fit the concept. So I'll put the numbers on in a minute. Here is point A is below the center. Point C is below the center. Point B is below the edge. Point D is outside the edge. So what we need to do at this stage is to figure out how points A, B, C, and D, exactly where are they going to fit. Well, we have to look at our calculations. Let's look at point A. Point A is what? X sub f over b is 0. Z sub f over b is 0.4. So let's take a look at that. So x sub f, I'm measuring, again, this is x sub f over b. Sorry, this is z sub f over b. So in other words, here are my axes of my coordinate system there, x sub f over b and z sub f over b. So we just have to take the x sub f over b and z sub f over b, put them on the chart. So point A is below the center, x sub f over b is 0. So I go down here, and what am I looking for? I'm looking for z sub f over b is 0.4, and let's read the numbers. So z sub f over b, that's 2, 1.5, 1, 0.5, and that's the 0. So I need 0.4, so there's point A. Point A is at 0.4. This is all approximate. Let's first put all the points in the right location, and then I'll show you how we read the number. So let's put on point B. Point B has x sub f over b of 0.5, z sub f over b of 0.4. So x sub f over b is 0.5. Point B is at z sub f over b, 0.4. Then we have point C. X sub f over b is 0. Z sub f over b is 1.6. So I'm at 0. I go down. Well, there's 1.5, so that's about 1.6. And then point D, I have x sub f over b is 0.8, z sub f over b is 0.5. So I come along here, x sub f over b of 0.8 is there, z sub f over b of 0.5 is there, so there's my point D. Okay, so all of the points are plotted properly on this chart. Now what do I read? I read the contour. All of these are contours. That is the value for each of those lines, and they represent the fraction of the surface stress. We're calling it sigma z over q is what they've shown it here. Sigma z over q. And so our goal is to read off these contours. So I'm going to read off the contour for each point. Well, point A is sitting right on the 0.8 contour, so it's 0.8. Now point B, the ones at the edge are the trickiest, but point B is here. If we look closely, it's between the 0.4 and 0.5 contour. So maybe it's 0.42 or something like that. Again, it's approximate. Point C is between what? Between the 0.2 and the 0.1 contour. It's a little bit closer to 0.2. So maybe it's 0.18. Again, approximate. Point D is also between the 0.1 and the 0.2 contour. It's closer to 0.1, so maybe it's 0.12. So we go to our table for the final answer, well, okay, 0.8 times Q for point A is what we read. So it's 0.8, the Q is 20 kilopascals. So we end up with 16. So point A here, so point A feels 16 kilopascals. The surface stress is 20 kilopascals. So there's a little bit of a reduction because it's down in the ground. It's not right underneath. The other, I got 0.45 for point B from the chart. So it ends up at 9. From the chart, you can read off 0.17 for point C. So we get 3.4, and then 0.13 for D gives us 2.6. So the key, once you've read the chart, this becomes quite simple. You just take your Q and multiply it times the contour that you get. Very straightforward. Okay, how do we use that in our settlement calculation? So how are we going to calculate the settlement of our structure, the various points of the structure? So let's take a look at this example. I'm going to have a case 1 and a case 2. Case 1, there's no basement. So here's my structure on the ground surface. No basement for case 1. Case 2, I've got a basement. You can see the building's embedded in the ground. It's 8 feet. We have an 8-foot basement. We're going to do both of these cases, and then we're going to see what the difference is. How do we handle them? In both cases, I want to find just the delta sigma V and the center settlement. So in other words, I want the settlement below the center of the structure. The weight of the structure is 625,000 pounds. Later, we're going to do the edge of the structure. What is the settlement at the edge of the structure? So if you look at it, my points of interest, well, it's important that you figure out the point of interest correctly, but I'll just indicate it. In this particular case, our clay layer is, both soil profiles are the same, from 10 to 30. That means our H, or my thickness, clay layer thickness, is 20 feet. And I want my point of interest at the center of that clay layer. So halfway between 10 and 30 is 20 feet down also by coincidence. Okay, so I'm going to have ultimately 2 points of interest. One below the center of the structure, one below the edge of the structure at 20 feet. So it's important to establish your points of interest so you do your calculations correctly. Now, I'm going to look at this. So that's the given information. Well, the other given information is the soil properties. Gamma D, gamma saturated, C epsilon R, C epsilon C, and I'm giving you the OCR for the clay. So I want to emphasize here the Z sub F. Now, that's the given information, but now you have to find the Z sub F. Z sub F, if you remember, I defined the Z sub F as the distance below the base of the structure. So, because I have a basement, in case 2, my Z sub F is only 12. Whereas when there's no basement, my Z sub F is going to be 20. Why? Because the distance to the point of interest from the base of the structure is only 12 here. So it's important that we recognize that that's one effect of having the basement is my Z sub F. Okay. Now, we have to calculate our Q. So here's my solution. I have to calculate out the Q. Well, case one is no basement. So the Q is very simple to find. It's just the weight of the structure divided by the area of the footprint. I guess I didn't... it's a square footprint, and the width is 25 feet. So that gives me an area of 25 square feet. So I get a Q of 1,000 PSF. Simply the weight of the structure divided by the area. Very straightforward. When we have a basement, well, what happens? Now we're assuming everything is done instantaneously, which of course in practice that's not possible to do, to build your structure instantaneously. So what we find is, and I've said that you need to know that dirt is heavy, and this is where it plays in. One of the main things that I want you to learn, almost if you learn nothing else from this class, know that dirt is heavy. If you move dirt around on a construction site, you can cause problems. It's very heavy. You try to hold up the dirt with a retaining wall, the dirt is heavy. The retaining wall stresses are big. So anyway, I have to account for the soil that I've removed, the sand that I've removed. Because in theory, if you can do it instantaneously, if you can remove, basically, my building weight is 625,000 pounds. If I can remove 625,000 pounds of dirt, then I have had no change in the stress of my soil below the structure, in theory. So the basement works in your favor because you're removing weight. And ultimately, your typical, if you remove 1 foot of soil, that is about equivalent to 1 story of the building. So if I'm building a 5-story structure and I put in a 5-foot basement, then I'm not going to get much settlement simply because I'm removing as much weight as I'm putting on. So that is the concept of putting in a basement. So in this particular case, our basement is, again, is 8 feet, about the equivalent of an 8-story building, approximately. This is all rule of thumb. So I'm going to subtract off. Well, the way that I'm going to do it is I'm going to take the volume of the sand that I remove times the density of the sand. That's the weight of the sand that I'm removing. Well, what's the volume of the sand? Well, the volume of the sand is the depth of the basement, 8, times the footprint area, 25 squared. That is the volume of the sand, and we've already said that the unit weight of the sand is 100. So that is the net weight that I'm putting on my soil, my clay. And I divide that by the area. So I get 200 PSF. Quite a bit less than the 1,000 PSF. So that is another impact of this, is that by putting in a basement, you've reduced your stress that the underlying soil is getting. Okay, so now I want to figure out my point A. So again, here's my point A in both cases. So I have to use my Boussinesq chart or my pressure bulb to figure out what my contour reads. Oops. And so okay, I guess I didn't, no matter. Let's look at our point A. Well, I have for point A, my ZF over B is 20 over 25. Why? Because if you remember, we did the ZFs already here. I've got a ZF of 20, ZF of 12. So I'm looking at my ZF over B, 20 over 25 is 0.8. And it's beneath the center, so I don't have to do my XFOB or anything like that. It's easy. For the other one, it's 12 over 25, which is 0.48, again, beneath the center. So I go into, so I look at 0.8 beneath the center and 0.48 beneath the center. So the numbers we want to remember right now are 0.8, 0.48. Going to go into my chart here. So I'm beneath the center, and there is 0.8. There's 1, there's 0.5. So, in other words, let's get it right here. That is 0.5, that is 1, 1.5, 2. Don't get confused as you're reading these numbers. And that means that this is 0.8 below the center, this is about 0.48 below the center. And what we're going to see, so the contour I read for this point is between 0.4 and 0.5. This one is between 0.7 and 0.8. And so I'm getting approximately for my contour here is about 0.45. It's between 0.4 and 0.5. And this other one is closer to 0.7 than it is to 0.8, so maybe 0.72. And so 0.45 times the 1,000 gives me 450 for case 1. And then I have 0.72 times the 200 gives me 144 for case 2. So those are my delta sigma V's. So I've got 450, 144. So notice case 2 has considerably less stress. Okay, so let's go for case 1, the center, and we set up our table. Again, the usual, we have t equals 0 minus, t equals 0 plus, infinity. And again, now we want the UXS first, because that's the hardest thing to get. Well, what's my UXS going to be? It's the 450. Because that's the stress that it has. So know this. Remember, the UXS at t equals 0 plus, remember the t equals 0 plus, is going to be due to the increase in stress. And of course, remember, it's 0 at t equals 0 minus. It's 0 at t equals infinity. So the only hard one is the t equals 0 plus one. So, and where did I get that number? Again, the 450 came from where? The 450 came from right there, my delta sigma, which came from my Boussinesq chart or pressure bulb times the Q, which is 1,000. So that is once you have that, the rest is simple. So my U water table, I'm not going to go through it. You can all get that. It's 10 feet down. My U is the sum of the UXS and U water table. And then now I have my sigma V. Well, I look at the picture, t equals 0 minus, t equals 0 plus, t equals infinity. I look at the correct picture. If you remember how the pictures looked, so let's go to the t equals 0 minus picture. And so here's my t equals 0 minus picture. There's no structure there. T equals 0 plus picture has the structure there. So I have to figure out what is point A feeling. Well, we already know it feels 450. So this is for the t equals 0 minus picture. You can all do that for point A. Then, so notice, 10 times 100 plus 10 times 90. Well, for the t equals 0 plus picture, I have the same thing, 10 times 100 plus 10 times 90. But then I also have the 450, which basically comes from there. It's the same calculation. So Now I have 2350 at t equals 0 plus. At t equals infinity, it's the same picture, so those are going to be the same. Same picture, same sigma v. And then my sigma v prime is sigma v minus u, so sigma v minus u, and I get these numbers. Notice that t equals 0 minus and t equals 0 plus, the numbers are the same. They're the same. And they should be. So that's a check on your work. And so this is my sigma prime I, that's my sigma prime f. To do my calculation, I need my, sigma prime p. I get that. We get that from the given information, and you can see that. How do we get the sigma prime p? Well, I'm given an OCR of 1.06. These are my C epsilon r, C epsilon c. So I use the 1.06 to get my sigma prime p, and I'll get my chart off of it. I'll do my chart. Now let's do the case 2. Case 2, now what do I have? Again, the UXS is the main thing you have to focus on. Everything else is easy. At t equals 0 minus, UXS is 0. At t equals infinity, UXS is 0. It's easy. At t equals 0 plus, that's the only hard one. How did I get the 144? Well, that came from where? That came from a couple steps back. There's my 144. Where did that come from? First, I calculated the 200 by subtracting off the weight of the basement soil, and then I look in my pressure bulb. I get the contour of 0.72 times the 200. So a little bit of calculation to get to the 144, but once I get it, I now have to put it in there. Okay? So it's there. The water table we've already done. I sum the UXS and U water table. I get the U. Okay, t equals 0 minus. We've already done this. It's 1900. T equals 0 plus. I've got the 1900 plus the 144. Same type of calculation. I get 2044, and then these two numbers are the same because the picture is the same. And sigma v minus u gives me sigma v prime. And what do I find? There's my sigma prime I, there's my sigma prime f, and again I need sigma prime p. And where do I get it? I get it from the OCR. So those three things will get me to my chart, which I'm drawing. So for case 1, this is case 2. We have the sigma prime I is the same in both cases. My sigma prime p is 1.06 times the OCR, 1276. I get 1353. So I put that on. I put on 1353. The 1276 goes to the left because it's less than 1353. For case 1, I had 1726. For case 2, I had 1420. Both of those points are greater than, so they go to the right of 1353. So when I look at my settlement chart, well, I'm going both. In both cases, I use both slopes. So what do? I plug in the numbers. You can see that this is going to be 1353 over 1276. 1353 over 1276. And I use the shallow slope, the C epsilon r. So 0.05 log 1353 over 1276, both of those are the same. Now I'm going from 1353 to 1726, so I have a log of 1726 over 1353. This one I'm going to have a log of 1420 over 1353. Those are the two there. And then, of course, when I do that, I have the C epsilon c, the greater slope, 0.28. So I get my epsilon v is 0.0309, 0.0715, and then my delta H is H epsilon v. The thickness of the clay was 20 times the 0.0309, 0.618 feet, 20 times the 0.00715, 0.143 feet. So what do we see here? The basement case has much less settlement than the no basement case. So the part of this illustration is not only to show you how to do this calculation, but also to illustrate that with this kind of foundation, if you build a basement, you have reduced your settlement quite a bit. So, and this is a technique that is used to reduce settlement by putting in a basement. Obviously, it costs a lot of money to build a basement. So, you have to excavate the soil, you have to build retaining walls a lot of times, and so it can be very expensive. So it's a cost trade-off in reality. So, okay, I will stop there.